preachy. All right, so multidimensional. So I promised just about 10 minutes of this. I have to spell it all out. Multidimensional quantum mechanics. There really isn't much to this. When we get to rotation, it'll be a little bit wonkier because rotation has to be done. Something can't rotate in one dimension. That's impossible. So when we start on rotation on next Friday, we're automatically doing multi-dimensional, but we're going to be doing it with cylindrical and spherical coordinates. So I'm going to tell you multi-dimensional with X, Y, and Z, and I'm just going to use a particle in a in a two-dimensional box instead of a one-dimensional box as an example. And so there's really nothing much to this. The way it works is, so I mean it's stupid simple. So minus h bar squared over 2m, double derivative with respect to x, and then guess what? Minus h bar squared over 2m, double derivative with respect to y. And I'll just stop there. You can do z too, but whatever. That's it. There you go. There's your Hamiltonian. There's your pure, remember this is a pure kinetic energy Hamiltonian. Pure kinetic energy Hamiltonian. And we often, of course, let's make this slightly easier to the eye by doing some factoring. And so just double derivative, but now you've got an x and a y. And the only thing that's a little wonky about this, so that's it. So we've done the alpha question.
You just distribute the wave function though to both operators?
Yeah. Now let me tell you how to do that. And I can't quite remember. Let me look again. What did I do on the homework? So I do a three-dimensional. So let me. I'm basically going to answer that. I'll do it in 2 dimensions. So you can almost just write this down. Okay, so this is the operator. There's nothing else to say. What about wave functions? How do you solve the wave functions? Okay, now this is where it gets a little funky. There's really only 2 ways you could possibly do this. You could sum them. Maybe there are some. Let me give you a reason why that actually does not work. Think about the expectation value. Remember that this is the thing that's real. A wave function isn't real. And one way I know that is I often see the letter I appearing in a wave function. Only a wave function, the absolute value of a wave function squared is real. And that's because it's a probability distribution. And probability distributions are real things. So let me write that down. Now I'm not going to assume that there's no letter I in it. There we go. And this is just childishly simple, by the way. The problem is that you get this guy, which is perfectly sensible. You get this thing, which is perfectly sensible. Again, knowing that these are probability distributions. If there's a letter I in it, it's been wiped out. It gets wiped out by doing this, which it needs to happen. Here's the part that makes no sense. There's a cross term. And from a probabilistic viewpoint, this doesn't make any sense. That you just can't do that. This can't influence the total probability. It says that the total probability of having some the total probability of some position in X space is influenced by the simultaneous position in Y space. Now think of a flat potential, right? This is a flat potential Hamiltonian. It doesn't matter where you are in X or Y, right? It's flat. You can be anywhere. But this says that where you are in X is influenced by where you are in Y, but none of it matters. So this is wrong, right? That's my point. There's another way to do this when you look at, if you apply an operator to this, which maybe that's what's on your homework, I forgot. If you apply an operator to a wave function of this nature, if you apply this to the Hamiltonian, you get whacked answers, right? It's just impossible. Okay, so the real solution, and let me just wipe this out because this is stupid. The real solution is that you multiply them. So it's not the sum but the product. And again, there's really no other way that this could possibly, there's no other way that this could possibly come about. There you go. All right, now, what do you do with that? Let me apply this to an operator. Let me apply this to kinetic energy and show you what that looks like. And I'll show you then how to solve it. Okay, so what does this do? I'm going to go ahead and do some algebra steps, but again, they're like super childish. So I have a method to solving these multidimensional things. First, take your operator and apply the wave function, and apply the wave function in this form, which we call separable, by the way. That's called a separable wave function, and that's because the Hamiltonian is separable. It's because I've got x's by themselves and y's by themselves. So all that means separable. And I told you about that actually in the extra hour last week. That one's kind of important. Okay, so what happens is when I apply x times y to this operator, it turns out that the y function can kind of just step outside of it. Of course, the x function is held up by this wall, and then I just permute. I permute that for the y. Hopefully I'm not forgetting any little squares or twos. I may be doing that. So remember, I often said that derivatives, kinetic energy, double derivatives, act like little walls to wave functions that they can't get past. But so now the reason this works is when you divide, when these things are a multiple, the y can just come right out. Okay, now step 2 in this is divide on left with the wave function, which of course again is x, y, the product. And what you end up with is, again, this is, if any of you recall the last extra hour, I actually was only talking about this. I'm just now putting it in I'm putting it with constants that you're familiar with. And it's just a lot to write out as well. And I'm hopefully not making any hideous mistakes. And I'm going to go ahead and remind you that all of this, of course, is equal to the energy. Okay. Now, like last time, each one of these has to be a constant. If these are not constant, and so since these sum, they're constants for when they sum to a constant. So let's call this one e sub x, and let's call this one e sub y. What's nice is that they're miniature Schrodinger equations. So it's like a separated, again, we call this separability. This is the property of separability. And one of the things that happens when you have a separable situation, you turn a big second order differential equation into maybe two smaller ones. And this one, here's one of x and here's one of y. And now you may notice that this is what we started on a month ago. This is here. Let me just keep working down on that. Let's do x, and of course y is the same. 1 over psi x minus h bar squared. I always put parentheses so you don't think that that's subtracted the minus sign, right? If you have this, then what you've got is something that you are hopefully sick to death of. See, I'm just multiplying. Remember that x is a subscript. Look at that, that's the Schrodinger equation. That's the Schrodinger equation for x. And so if we're doing a particle in a box, it's the same damn thing. The wave function of the x is exactly what it was before. 2 over, but now here's the thing. I'm going to have to, now that I've got two dimensions, I've got to start being more careful. I have to note that the length in the x direction is going to be L sub x. So I'm going to have to be a little careful. The quantum number is going to be n sub x. And there you go. And likewise, now this solve y is, it's just the same thing with a bunch of y's as opposed to x. Now, I'll explain a little bit of what I mean by Lx and Ly, not that that's not obvious. There you go. I mean, yeah, that's it. I told you, this is like unbelievable. It's stupid easy. Of all the questions I could ask, this is unbelievably easy. Question?
Should the other L have a summit? Other L.
Oh, yes, you're right. It's all the same thing. There is no L. There's no L by itself. It doesn't exist in this two-dimensional problem. Yeah, thanks for pointing that out. Okay, so there you go. Yeah, and of course the energy is, here, let me draw the potential surface. So again, I'm doing a particle in a two-dimensional box. So there's an Lx, there's an Ly, and of course we can make those the same length. That just makes things way easier. So there's your potential surface, right? Again, I would make, to make the questions easier, I would make the lengths the same. And what does the ground state look like? I'll do my best to draw it, but of course it's going to be it's going to look something like this. Hopefully I'm not choking too violently on that. Yeah, you can, that's not bad, right? Here, let's see how big a jump I can do, some shading or something. Yeah, so that's the ground state. Actually, no, not quite, right? I kind of drew that little Gaussian shape, and it's really more half sine shape. So I kind of screwed that up a little bit, but hopefully you see the point. And the energy, now let's apply the Hamiltonian to the wave function. What you end up with is minus h bar squared over 2m. Oh crap. Damn it, I actually forgot what this turns into. Oh wait a minute, maybe if I look at my answers, I actually have it here. No, yeah, sorry. You can do some factoring. There's some 2 pi's and whatnot. So there's a little factoring here, but it ends up being, there's really nothing through this in there. There you go. And the other thing that's kind of neat is that you see that you introduce degeneracies. Of course, the same deal is true for the quantum numbers. You now have 2 of them. Notice that you now have degeneracies possible. You can have y equals 2, n equals 1, nx equals 1. So ny equals 2, nx equals 1 is the same as nx equals 2, ny equals 1. That's a little subtlety. It's true, and you might want to put a little star by this. So this is kind of important. I think we're done with this. You might want to put a little star by this. So multi-dimensions equals degeneracies. So now, of course, degeneracy is when 2 states have the same energy. And you simply cannot muster that in 1 dimension. So think of the 1-dimensional particle in a box where you have n sub x, n is 1, 2, 3, 4. How can you, every state has a different energy. But when it comes to multi-dimension, you can end up, the reason that you can have degeneracies is that you have sets that are equivalent to other sets. Now, this is what I just said. I'm just writing it in a nice mathematical form. Right, so the 2-1 set is equal to the 1-2 set, essentially. They would have the exact same energy. Now, that's kind of a little factoid, but I am going to point this out a couple of times. You're going to see this. When we get to rotation, you start seeing more degeneracies. And that's because we're going to start with doing rotation in a plane. So something, get a string, get a cat by its tail, and just swing it around. And I got your attention now. It's automatically only in 2 dimensions, right? Even if I swirl it at an angle, all I have to do is adjust my coordinate frame, and now it's in 2 dimensions. And you find not too many degeneracies. If you can swing things in 3 dimensions, right? You can cause things to do like this, and hydrogen atoms do that. This is a D function, by the way. When you rotate and you force something to rotate in 3 dimensions, you actually pick up more degeneracies as a result. So degeneracies are only, degeneracies, by the way. The S state has no degeneracies, 1s, 2s, 3s. P states are degenerate, px, py, pz. D states are degenerate, more so. X squared minus y squared, dz squared, right? There's 5 of them. And that's because they're in 3 dimensions. That wouldn't be possible otherwise. Question?
When you write the expression for the Hamiltonian of the wave function, are we all supposed to have the wave function multiplied?
Yeah, sorry. Yeah, of course. I did this the eigenvalue way. And I think this is similar to what I had you do on the homework. So basically, I think I did that in 3 dimensions, and this is 2 dimensions. It's not hard to tack on a z to what I just showed you. Other questions? You're okay? Well, there's plenty of time left, and if you folks want, if you don't have any other questions or want me to just do some homework, I can show you how to do position eigenvalue. It's a graduate level concept, but was a question?
Yeah,
You want to see?
it's just about the graphs.
Mhm.
Like for question number 4, is this a barrier that goes between?
Yeah, so let's look at number 4. And so what I did on the homework, by the way, as I mentioned to you before, look at what happens with a free wave. Double derivative in x times wave function is equal to energy times the wave function. And hopefully at this point, sine, cosine, e to the ikx, e to the minus ikx is not like particularly mind-blowing at this point. But regardless. And then I put in double derivative of x plus x squared, what we just did. And I can tell you again, the derivation, instead of being derived in just 1 or 2 steps, it takes like 50. So on the homework, I have thrown every one of these flat potential problems I can humanly run at you, because if I start getting more complicated, it goes from like being done in just 1 or 2 steps to being done in 50. Just by throwing in a little curvature or something, all of a sudden it's like impossible. So number 4, well, I do actually have some curvature, but I don't really have you, I basically gave you the answer where with the potential on the left, I don't know that that's coming through very well. That goes to infinity, right? So you have, I kind of designed, I don't know that what I've done is exactly correct, but there's a region 1, and then the potential starts to rise, which, by the way, is kind of like half of a, it's like half a vibrational potential. So you have a region 2. Now, the first thing is you start applying boundary conditions. So if the left half goes off to infinity and it's positioned at 0, I guess I left you some possibilities for the wave function, didn't I think was the right question?
No,
What's
it's a
the-
different one. The one you're thinking of is where you have to.
No, this is, no, I'm doing this one. So yeah, no, we're describing the same one. What's your question then?
It was just about the graph. It went all the way.
Yeah, it goes to infinity. So given that this is a flat region, your wave functions are either sine, cosine, e to the ikx, or e to the minus ikx. So which one is it? And of course they tell you.
You said it was fine.
Right, but that's how you could have known that this goes to infinity. Because you absolutely have to stop. It has to stop here. Cosine, e to the ikx, e to the minus ikx, none of them stop at 0. Only e to the ikx minus e to the ikx, which is a sine function. That's why that guy is what it is. And then I have you try to pair that up with a vibrational type of field. Yeah, something like that. Okay, does that answer your question? Okay, so, and again, remember, you can email, come by office hours. Okay, so, just to immerse you into quantum, I did want to this is just kind of neat, because when I was your age, I tended, maybe it's one of the reasons I got into what I did, it kind of made me angry to know, and so, what most people do when they teach this class, the fact that x is unsolvable, it actually is, I'm about to show you, but from everything you have ever seen in your life, this should never be solvable. X is always x. How do you turn this into an eigenvalue? And I'm going to call that x prime, by the way. That means like 5, okay? 5 nanometers. How the hell can this ever happen? You know, I think I even asked some of you this, and you said, well, you just decide that it's 5 nanometers. And oddly enough, that's actually almost correct. That's, when I show you the solution, that actually is part of it. But regardless, still though, x added to a wave function naturally had to turn into a number, and you should, how the hell do you do that, right? Now, when other people teach this class, the solution is never to bring this up, right? But I have a problem doing that kind of stuff to my own detriment. Never bring this up. Notice that every wave function you've ever seen, sine, cosine, e to the ikx, none of them are eigenvalues, are eigenfunctions. Not a single one of them is an eigenfunction of the x operator. You have not seen an eigenfunction of the x operator yet, even though they all have x in them. But remember, that's irrelevant. The thing that makes something an eigenfunction of an operator is to observe this behavior. It can, you know, just because sine and cosine don't do this doesn't mean that you still can't use sine and cosine. Besides, they were the eigenfunctions of the Hamiltonian, which has x in it, but is not just x, right? So again, that's why I actually want to show you this, because there's some value into, the more you absorb this stuff, the more it kind of starts to make sense. And I mentioned to you, the thing about quantum is you really just want to see it over and over and over and over and over again. I certainly would like to explain it as well as I can the first time, but I don't think there's a person alive for whom that's going to work. So you just want to watch this stuff over and over and over and over and over again. Okay, so how in the hell do you solve this? Here's Dirac. So when they started doing quantum mechanics, they realized that this was a problem. And Paul Dirac, no one had this mathematical paradigm before. He came up with it to solve this. So now get this, watch this. Ta-da! That's how he did it. Why? What he's looking for, actually I forgot, what the hell is this? Okay, so what you're looking for is a function that equals 0 when x is equal to a certain value. Now remember, x is x, seriously, I can't simplify that. X is x, y equals x, you know, a line, it's the same old x you've ever seen. X prime is going to be a number like 5 nanometers. Remember, it's units, right? So we'll be working in nanometers. Okay. When x is 5 nanometers, this function becomes 0. Sorry. I messed up. Let me read my notes. Let me see how this messed up. When x is, yeah, my bad. Okay, so here's the logic. Sorry. Just need to prepare a little more. It's Friday, right? Okay, so here's the wave function. The wave function is 0 when x is not equal to x prime. Okay, so you see what he does? 0 equals 0 is a solution. But that's because unless you're at x prime, this is 0. So I have 0 equals to 0. But if you're interrogating this thing at x prime, then the function is not 0. in which case this x, this is going from like minus infinity to infinity. Only when this is at x prime do you get a non-zero equals 0 solution. Okay, kind of see what I mean? So again, the eigenfunction of this operator is 1 that is 0 everywhere except x prime. Right? Because when you're outside of x prime, when x is not x prime, you've got 0 equals 0, which works. When x is at x prime, then the function is not 0, but then look, then the eigenfunction magically worked. Okay, so anyway, that's the idea. It might help to show you what that looks like. Let's see. Okay, the definition is called a Dirac delta. It's a Dirac delta function is what does that. Now, here's where this gets really funky. The reason this is going to work. It only works in an integral. It is defined via an integral. So I know that we have functions and then we integrate them. Sometimes we take the derivative. Sometimes we have functions, we integrate them. The Dirac delta is an integral. It doesn't exist outside of an integral form. Now that's kind of funky, but that is what it is. The way it's defined is this way. So it's like normalized. Right? So I mean, it kind of makes sense. I'm not squaring it, but anyway. So Dirac says that this is what it looks like. Okay, now let's plot it. Okay, so basically the area is 1. And let's look at 0. Okay, one way to make something have an area of 1 is to build a box with an area of 1. And if you integrate it, you'll get the number 1. Okay, but Dirac says narrow it down. Dirac says narrow that sucker down. Okay, so imagine Dirac is showing Einstein this for the first time, which actually probably did happen. Again, the x-axis, this is x equals 0. Okay, all right, so what? Now what Dirac says is you actually infinitely narrow. Okay, so you see what happens is the Dirac delta function is a function. It's like this, but make it more and more narrow till it's infinitely narrow and centered at 0. That is what a Dirac delta function is. It's a spike at exactly 0. It's a spike at exactly 0. It only exists at x equals 0. Now, of course, it's infinitely high, but you integrate it, you'll get the number 1. So it's kind of an invented thing. You actually can't, there actually is a way to turn it into a function. It's like a sine over an x or something. You can't actually turn this into a functional form, but let's not worry about that. Let's define it by these properties. It is infinitely narrow, centered at 0, and integrates to 1. And that is the eigenfunction of the x operator. Now, how does that work? Okay. Let's take, so that's one eigenfunction of the x operator, but let me make this relevant to all the other stuff you've learned. Let's take the wave functions you've seen before, like sine and cosine or e to the ix. Let's make it, I'll just call it f of x. Here's how a Dirac delta function works to make those work. Okay, let's take a wave function. Now remember, this is not an eigenfunction of x. You know, x times sine is not 5 nanometers times sine. Those are not the same. All right. To make this an eigenfunction of the x operator, you do this. You take the wave function and you multiply it by the Dirac delta function. But you've got to recall that you can't just write this down like that. As soon as you put that down, you have to put this. You are automatically obliged to put that. You don't have a choice. Remember I told you, Dirac's delta function requires an integral to be there. It's defined only in the form of an integral. Now, the solution to this ends up being, so Dirac's delta function, now think about this. Dirac's delta function, as you evaluate this integral, remember that you're basically looking at the area under the curve. The contribution to this is whatever. Maybe it's a sine function. Just plug in sine of -5, -4, -3, -2, -1, 0, 1, 2, 3, 4. Fine, you get a value. But this SOB is 0 everywhere except x equals 0, right? So you see what that function is doing? This thing is killing this by being 0, except at x equals 0. That means that I can take the wave function out at point 0. I can factor it out because practically, it doesn't matter what this is. This SOB is 0 and it's killing this off except at point 0. Okay, that means I can factor that out, and that leaves me the Dirac delta function, which is, right, which is 1. See, it's snarky, huh? But it works. So that's how you do it. That is the way that you write these things with with these guys. Now, what did I want to show you? Okay, so let's see. Now, let me show you some properties of this. And let me show you how you can still do things like expectation values. Okay, so let me go further with this. Okay, now let's, so this was a wave function. It could be any function, including an operator, right? So I've shown you what the wave function is. Let's go back to looking at the operator, right? The operator x. Okay, so let's get the x operator and operate on its eigenfunction, which we now know is the Dirac delta function, right? Now, as soon as I write that down, what's that?
But it's not a function, it's a vertical line, right?
Well, now
vertical lines
remember,
can't be functions?
now hold on. As soon as I do that, remember, I'm automatically obliged to do this, right? You can't just be writing this down. You can't write that down like that. It's not part of the rules. The rules are, as soon as you invoke a delta function, you automatically have to put an integral sign. It's defined that way. There is no function. There is the integral of a function. It exists as the integral of a function. It does not exist outside of that. So I know, remember, you can take sine functions and integrate them, fine. This is a function that only exists as an integral. It has no meaning outside of that. Right, so operator times function. Now again, I have to, as soon as I see that down, I actually have to write that down. Otherwise, I'm actually screwing up. And what you end up with is, now again, this SOB makes x, this is 0 except everywhere at x equals 0, so I can factor that out. And then I've got this thing, which is 1, but it doesn't matter, it's 0. There you go. Okay, 0. And of course, I guess I can still put in my Dirac delta function. So there you go. I've got operator function, eigenvalue function. Okay, but now a funky thing you may have noticed is that I'm only able to query at x equals 0. So this operator, this unique solution to the x operator, which returns a value times the function, right? Operator function, value function. It actually worked, but it only returns 0. How can it make it not return 0? What can I do? Now remember, the innards have to be 0. Let's make it 5 nanometers. How would I do that?
Plus 5?
Well, actually minus 5. Here you go. Yeah, exactly. Now again, as soon as I do this, not fair. I have to integrate it. It does not exist outside. Now, again, only when the argument of the delta function is 0, which means that x is 5, do you get which again is 5 times the function. See that? Operator, function, value, function. It works. Question?
I don't know how to word it, this question right, but, so you say you want 5, so you want x to be 5, so you put 5 into the function,
Yeah.
and then you get 5 out?
Yeah.
Doesn't this seem like, it doesn't make sense that you already know the answer that's coming out when you
What-
go into the problem? So
Okay,
you're
okay.
doing all this work to get back to where you started?
Now here's the thing. What you're actually saying is you don't like how the solution looks. That's what you're actually saying. Now let me point out why. Let's do a particle in a box wave function. All right. Now I do this. What's the answer? Well, you see, it's a ridiculous question. You see, the wave function is defined from 0 to L. So how can you ask it where it is when it exists over a range of places? Now remember, I did this before. How much money is in your pocket? So I want to know how much money you all have. How much money is in your pocket?
$15.
$15. Okay, so all of you have $15. No? Well, but I don't understand. I just operated on you and got the answer. I want to know how much money you all have, and I operated on this one point, got an answer. Are you telling me it doesn't apply to the rest of you? It doesn't, right? So is what I did sensible? In terms of answering this question, was it sensible to query a single point and say, how much money do you have? I can get an answer, but what's that got to do with the rest of you? Which is what I'm really trying to get to. Right? So if I'm asking a single point on something that exists over a range of points, that's a stupid question. It's just like I want to know how much money you have. Why am I asking just one point? Why am I only querying one point? It's a dumb question. It's a dumb way to go about it. Really what you want is, so dumb questions get dumb answers.
Yeah.
Right. So you see, this is actually useless. This is useless because you actually have to decide the answer before you solve it.
Yeah.
It does have the benefit of working, but you have to know the answer before you solve it. So if I want to know the wave function at position 0.5, then the way to do that is this. Right, so now I've written the wave function correctly. This is the correct wave function, and the answer is, it works. I guess there's still, there's still a delta function there, but right. I had to decide ahead of time where I was asking, only to get back exactly what I asked to begin with. What the hell is the point? Just like asking one person how much money do you have has nothing to do with the rest of you because there's a range of values, right? The point, if that's confusing you, you should be confused because it's a nonsense. It's nonsense. So it is neat that there is a way to do this, but it ultimately is nonsensical and not really useful. And that's it. But let me show you one last thing. I know I only have a few minutes. Where it actually is useful, is that you can still do this. Okay, so now note that when I asked, right, so when you're doing this is a stupid thing. It doesn't mean anything. It's like why are you asking that when you already know the answer? What you really want is this. Right? If I want to know how much money you all have, I can't query one person. I have to ask you all, and then I can get an average, and then that's meaningful. Now I'm asking the right question. Now here's the neat thing about this, is that let's do this. And you actually know how to do this already, right?
Yes.
Right. You actually already know how to do that. Wave function squared, which is a probability density, times the thing you want the average of. So you already know how to do this. We've basically been doing this since Maxwell Boltzmann. Let me point out something that's kind of cool though. The way you do this actually is, let's write down, let's do that, because I'm doing an average value, but I'm going to be using eigenfunctions of the x operator. And that means that I've actually got a triple integral, a triple by the way. I've got is that right? Actually, I'm a little confused. You actually, I have to keep track of these different x's. I actually have to do it this way. So notice it's kind of hideous. So I have two wave functions. I have two wave functions and two Dirac deltas. And so that means I actually have two integrals. But because I'm doing an expectation value, there's actually three integrals. Now it turns out that here's an ID, here's an identity by the way. And this is a little hard to prove. It's just some algebra. But let me just show you real quick. When you have two delta functions, see I have two delta functions, that's why this is a little bit funky. It actually turns into this. Now this is about a 5-step little algebra proof. You can actually do it knowing what you already know. But what this does is it turns this triple integral into a double integral. So I can get rid of one of the integrals. Minus infinity to infinity. So I get this one times the operator times the first one. I think I made a slight mistake somewhere. No, what have I done? I think this ends up being, so if you do the integral of x2, what you then end up with is, you end up with one integral. So all the x2s turn into x1s. That's all that happens. Which is exactly right. Which is exactly that. So anyway, here's the point. Here's the point. These Dirac delta functions are the eigenfunctions of position, and you've seen me work that. If you plug them into if you want eigenfunctions of particle in a box and e to the ikx, all you do is take all the jazz you've already seen and multiply it by a Dirac delta function. And then it's an eigenfunction of position. But it doesn't matter, because what ends up happening is this complex representation, which is the true quantum mechanical way to do this, filters back into what you already knew. So again, that's the take-home message, that if you want to do x problems with x eigenfunctions, that's totally okay. You end up with these delta functions, you end up picking up an integral for every one of them, but the operation of those delta functions filters back down into the expressions you've actually already been working with, and you get the same answers. So anyway, I think I might have messed up some ones and twos here, but anyway, that's the idea. And